Hello, welcome to section Functional Programming with F#. In this section, we will learn functional programming more thoroughly. Firstly, we will look at composition, which is a key aspect of functional programming. Composition is about combining smaller functions to build bigger programs. Next, we will look at partial application. Partial application is about we are only passing some of the parameters to the function and the function yields another function to us. You will see examples to this. Next, we will see immutability and data structures. As we have mentioned, all data structures in functional programming are immutable. And of course, this brings other challenges. We will see how functional programming and immutability deals with challenges, and we can have efficient data structures. After that, we will look at records and equality. In functional programming, we don't have objects. Instead, we make use of records. Of course, in terms of CLR, these records are objects. However, from F# point of view, they are more like database records. And we will see examples for referential transparency. And then we will look at discriminated unions. As we mentioned, functional programming is about building bigger blocks from smaller blocks. Once we design our types, it is possible to combine these types to build bigger types. And finally, we will look at options and null value. As you would remember, we called null values as a billion-dollar mistake, and instead of those, we make use of option types. Now let's learn about composition. Composition is a key aspect of functional programming. As you would remember, it is about combining smaller functions to build bigger functions. In order to do that, the functions has to have compatible input and output parameters, so that one of the function's output parameter can be input to the next function. Let's see an example for this. Here, let's see an example for composition. Here, as convenience, I define a const function which makes use of the static method of the list class. Then I define a reduce function. Reduce function acts like an aggregator. It takes three parameters. The f is the aggregation function, x is the initial value, and there is hidden list value. It is hidden because I make use of this function keyword, and it allows us to pattern match the last hidden parameter. So this is essentially the same width. If I add a L parameter and match L with, because I use this function keyword, I can delete this and write function, and F# allows me to imply this fact. And basically I'm evaluating two states. If my list is empty, then I'm returning my initial value. If it is not empty, then I'm basically separating the first parameter of the list as head and the rest of the elements of the list as a tail. Then I'm reducing the tail part first. Actually, this operator allows me to evaluate the right hand side, then allows the function to be applied. So all the tail part are reduced here by using f and x. Then when I have an output, I apply f head along with the reduced tail. Here I define an add function, which is basically adding two numbers. Then I define the sum function. The sum function actually makes use of this reduce function. Notice how easy to define such a sum function by using aggregation. So I make use of my add as a first parameter to f and 0 as my initial parameter, and my sum function is ready to sum all the elements of the list. And to make use of it, basically in this statement, I'm passing 1, 2, 3 to my sum function and printing the result. Let's see this in action. I'm opening my integrated terminal. All right, .NET build and .NET run. As you see, the result is 6. We can similarly define a multiply function. Let multiply x, y is equal to x times y, and then let mul equals reduce multiply, and our initial parameter is 1. And to test our function, let's make use of our mul. Mul, and let's add a fourth parameter to make the result different. Save it. .NET Build. Run. Actually, this is a good example about how to build bigger functions from smaller functions. Let's add another function. Let any true equals reduce or false. Actually, this parenthesis is a convenient way to define our functions. This is actually equal to let my or equals. So these two are the same, and I could have used my or function instead of this parenthesis, but it's a shortcut. This function allows me to check if any true element is in my list. Let's test this. True, false. Actually, you don't have to run .NET Build. .NET Run already implies .NET Build. Let's save our file and run it. If I make this false, then the result is false. Let's define another. Let all true. Basically, now I'm ending all elements in the list by specifying initial value true. And let's run. And if I make all of them true, and the result is true. As you see, by using our reduce function, we can generate a number of functions, and this is very convenient. We are not limited to mathematical or logical functions. We can also define let append a b. Basically, we are implementing a function that appends to list. Reduce cons ba. Note that we are getting an error because the cons function actually deals with tuple, which doesn't fit into our case. So in order to fix this, we can do this is because list.cons takes a tuple, but we need a 2-parameter function. And making this change basically fixes our error. And now we can try. Append true, true, false, false. Save our file and run. As you see, our append function successfully appended 2 lists. Now let's write a function that doubles all elements of a list. Let double and cons num list equals cons 2 times num and list, and then let double all equals reduce double and cons with empty. And if we test this, double all, 1, 2, 3. Notice our reduce function is not only useful for reduction, but also can make transformation. And this is a good example. We can further modularize our functions. Let's define let f and cons fl list equals cons fl list, and then let double becomes n 2 times n. And finally, our double and cons function will be let double and cons 2 equals f and cons double. Now let's try this function. And let double all 2 will be reduce double and cons 2 empty list. And if you run this version, everything still works fine. We can even do further modularization. Instead of this, we can define basically this is a composition operator. So we are saying whatever output comes from f, send it to cons directly. No need to do additional parameters. If the output signature matches to the input signature of this function, then our functions will work fine. Let's run. We can even do the following. Reduce double cons and with an empty list. And if we run, we'll see the same result. This is because we are doubling each element one by one and then do the construction of our list by using this composition operator, which is basically fusing two functions into one function. Doubling and constructing a list function fused as one function. And even from this, we can define the famous map function as let map f reduce f cons empty list. And then we can rewrite our double function as map double. And we run our code. Now our code becomes more and more generic because we can specify whatever f, in this case it says double, from outside. Although this looks complicated, this is a good example about how to build bigger functions from smaller functions.